Okay, here we have an artery which is blocked, and we have some pressure measurements. We know something about some density and speed of the blood flowing, um, when it's not blocked, and we want to find out how much of the artery is blocked, what the blockage kind of percentage is here. So let's just kind of draw a figure and write out what we have known to us. So here's kind of here's our artery like this. We'll say that it's all going horizontally. I'm not going to deal with a height difference. It would be a very small height difference anyway. And then I have some sort of blockage in it, right? So artery, and then there's like blockage, some stuff in here, right? Okay, so let's say that we have some cross-sectional area before the blockage, which I'll call area 1. And we have some speed before the blockage, which I will call V1. And then after, in the blockage here, we have some new area, A2, and there's some new speed, V2. Okay? Now, we make some pressure measurements, or the medical technician does, and she measures that the blood pressure in the region of blockage is 1.2 times 10 to the fourth pascals. Or sorry, that's before the blockage is 1.2 times 10 to the fourth pascal. So that's pressure 1. So pressure 1 is equal to 1.2 times 10 to the fourth pascals. And then in the blockage, that'd be pressure 2. This is going to be 1.15 times 10 to the fourth pascals. A little bit less there. Okay. And so we know, just from like Bernoulli's equation, and it's sort of counterintuitive, but the faster it moves, the lower the pressure, right? So automatically we have right here, we can kind of see the general way that we're going to go about this, actually. We have a pressure difference, right? So a lower pressure here means that the speed through 2 will be greater than the speed through 1, right? This is what we know from Bernoulli's equation, from really the work energy theorem, right? So, there's more energy in the flow if there's less in the pressure, less work done with the pressure. And so if it's going faster in V2, we also know from the continuity equation that this would mean that area 2 would have to be less than area 1, right? So this is what it means. So then I can find out what area 2 is in terms of this stuff, and then we'll do a ratio of area 2 to area 1, find out how much blocked it is. Okay? So we would think, it makes sense that the pressure would be less in a region of blockage because smaller area, therefore faster speed, therefore lower pressure. We also know, so V1 was given to us as, 30 centimeters per second, right? So, that's going to be 0.3 meters per second. Pascals is in newtons per meter squared. So it's important that we keep everything in the metric system, right? And so, in standard units. So V1 is equal to 0.3 meters per second. And the specific gravity of this patient's blood is 1.06. So I didn't cover specific gravity in my lecture videos, and I would kind of just give you the density in on an Inquisitor exam or something. You might have seen this in your chemistry classes, but specific gravity is the ratio of the density of something to the density of water. So fresh water, that is, at like, I can't remember exactly what the temperature is, but it's a specific temperature because the density changes with temperature, right? This is actually one of the big things with sea level rise. One of the big reasons that the sea level rises with the increasing warmth is because the ocean expands as it gets warmer. Anyway, so the specific gravity is a density. It's a ratio of the density to the density of water, right? So if you want to find out the density of, this is blood. So if I want to know the density of blood, this is going to be the density of fresh water times the specific gravity, right? Something that has a specific gravity of 1 is the same gravity as water. Something that is a specific gravity less than 1 would be lighter than water, it would float, and more than 1 would be heavier than water, it would sink. And so we have, anyways, the density of blood here would be specific gravity 1.06 times the density of fresh water, which is 1,000 kilograms per cubic meter. And so this is equal to 1,060 kilograms per cubic meter. Okay, so there's the density of the blood. All right. So, we can use here, if we look at this, Bernoulli's equation has pressure, speed, mass, density, gravity, and height, right? I'm saying here that the y1 is equal to y2. So they're the same height here. And so we have everything that we need in order to set up Bernoulli's equation and solve. So, or really this would be, the work energy theorem for a fluid, right? That's the Bernoulli's equation. So at point 1, we have the pressure at point 1 plus the kinetic energy associated with the kinetic energy, 1/2 rho V1 squared plus rho GY1 is equal to the pressure at point 2 plus 1/2 rho V2 squared plus rho GY2, right? So since y1 is equal to y2, these terms in the density didn't change. These terms will end up canceling out, right? So we know V1, we know pressure 1, we know pressure 2, and we know density, right? So the only thing we don't know is V2. So we can solve for V2 is going to be plus or minus the square root, but we'll just take a positive velocity here. And this will be 2 over rho times, this will be P1 minus P2 plus 1/2 rho V1 squared. Okay, so plugging in all these values, I'll go ahead and plug them in here. This is going to be 2 over 1,060 times pressure 1 was 1.2 times 10 to the 4th minus pressure 2 was 1.15 times 10 to the 4th plus 1/2 of 1,060 times V1, which was 0.3 meters per second squared. And so the speed 2 is equal to 1.017 meters per second. Okay, so that's flowing quite a bit faster actually in the region of blockage. V2 is 1.017, V1 was only 0.3. It's going, over 3 times as fast. So it must be pretty significantly clogged, because we know from the continuity equation, we know that the flow rate is the same. So A1 V1 is equal to A2 V2, right? So if I just wanted kind of a ratio of how much blocked it is, or actually, let's just get a ratio of A2 to A1. So how big area 2 is to how big area 1 is. How much is open? Let's do that. So ratio here, area 2 to area 1, because I'm not given area 1, right? But I can get a ratio, because all we want to know is what percentage, which is the ratio, times 100%, right? So A2 over A1 is going to be V1 over V2, right? So that's going to be 0.3 divided by, what did we say, 1.017. And so this is equal to 0.29. So, this is saying that area 2 is only 0.29 of area 1. So only 29% of area 1. Basically. So this area when it's clogged is 29% of the area when it's not clogged, or it actually asks us to find out, the percentage that is blocked, right? So you know, if it's 29, it's only 29% as big, then 100% minus 29% is 71%. So we can say here that this is 71% blocked or clogged. Okay, so yeah, pretty clogged artery there.